Hi everyone, we will solve worksheet 11 today. So it's about trees. For the first question, we will decide if the given graphs are trees or not. First of all, they should be, if some graph is a tree, it should be connected, okay, and it should have no circuit. So for the first one, we see it's connected. And obviously it has no circuit, but for example, if there would be an edge between them, so obviously we would have a circuit in it, okay, so it wouldn't be a tree, okay, so but it's connected and there's no circuit, so it's a tree. And this is not even connected, right? So it's not a tree. Okay, and what about this? So it has no circuit and it is connected. You can connect any edge using this vertex, for example, this and this, right? And this and this. Okay, it is a tree. So the last one is not a tree, and these two ones are a tree. Okay, here is an answer. So what about the second one? We will determine these parts. So we are given this tree, right? What's the root? It's A, right? And okay, let's write it again here. So here we have the answer A. Okay. Now, what are the internals? So here we have an explanation here for B. It's a vertex that has a child, right? So what's a child then? The vertex which is found below of the vertex, of some vertex. So for example, N is a child of F, okay, and F is a parent of N, okay. So what's an internal again? It's a vertex that has a child, right? So we need to find the vertices that has a child. For example, B has a child, E, and also F. F has a child, L, right? So B is one of the internals, and F is also an internal because it has three, for example, three children, so it's an internal. And C is also an internal because it has two children, right? And H has two children. It's an internal, and also T because U is a child of T, and Q because S and T are children of Q, and J because again, and D, right? So these are internals. Okay. And sorry, what are the leaves? A leaf is a vertex again, which has no children. Okay. So we will find the vertices that has no children. What are they? L, M, and obviously E, G, O, P, I, R, K. G is not a leaf because R and Q, for example, children of J. And finally S. Okay, these are leaves of the tree. So we'll find the children of J. So here is J. What are the children of J? Q and R. Let me clear first so you can clearly see the answer here. R and Q are children of J. Okay. So there should be a direct edge between them. Okay, because T is not a children of J because there is no an edge like that. Okay, if there would be an edge like this, there would be a circuit then. It wouldn't be a tree, right? Remember that. So what's the parent of H? It's C, obviously, right? The vertex before H on the above, through the root, okay? And what are the siblings of O? It's P because they have the same parent, right? Here you see, before we had C, right? Here, C, the parent of C. So, and the sibling of O is P, as I said before, because they have the same parent H. Okay. And for example, these are siblings too because they have the same parent. Okay. And what's the ancestors of M? So here is again the explanation. Oh, I didn't write that. For G, they are F, B, and A. Let's look at on the tree. Sorry, we are checking for ancestors of M. So M is here. Its parent is its ancestor, and the parent of this parent, which is B, is also grandparent. You say it's also an ancestor of M. And here we have A, which is the root of the tree. Obviously, it's also the ancestor of M. Okay. What about U, T, Q, J, D, and A? They are all ancestors of M. Okay. Now, what are the descendants of B? Here we have B, E, F, right? L, M, N. Okay, they are all descendants. Let's check the answer here. For H, descendants of B. They are not only F and M. I made a mistake there. As I said before, they are E, F, M, N, and L. Okay, because one of the ancestor of L is B, right? So L is a descendant for B. Okay, so it's not only F and M, also E, L, and N. So there is a mistake there. Okay. So what about the third one? We will draw a subtree, okay, using this tree, okay, of this tree, such that the subtree that we will draw has root A, okay, and C and E. So here we have the answer for B. The subtree which is rooted at C is this. So here we have this, for example. Okay. So this is a new tree itself. Its root is C, right? And it's contained in this tree, the bigger one. So it's a subtree of this given tree, where the root is C. Okay. Remaining ones are homework. Let's look at 4. So how many non-isomorphic unrooted trees are there? We want them to have 3 vertices. So let's write all graphs of with 3 vertices. So if there's no edges, it should look like this. The graphs with 3 vertices that have no edges are isomorphic to this one, right? And with 1 edge, with 2 edges, and 3 edges. Now, this is obviously not a tree because it's, for example, not connected. And this is also not connected. This is not connected either, so it's not a tree. We don't care about it. Then, so this is, what about this one? It's connected, right? Any 2 vertices has an edge between them or a path between them, right? So there is no circuit either, so it's a tree. And what about this? We have a circuit, obviously it's not a tree. Then all all trees that have 3 vertices are isomorphic to this one. Okay, so there is only one non-isomorphic tree which has 3 vertices. Okay, so because it says that any tree that you can write with 3 vertices will look like this, or if you rotate it, it will look like this. It is isomorphic to this. For example, you can draw it like this, but you can obviously find an isomorphism sending this to that vertex, this to that, and this to this. Okay, it will be an isomorphism between them. So any tree with 3 vertices is like this. Okay, and what about B? Now we will find the, again, non-isomorphic rooted trees with 3 vertices. Now here, before we solve that, the only tree with 3 vertices is this one, right? With 2 edges. So now we want it to be rooted, right? So it may be even like this, look like this, or look like this, right? So it says that obviously there are only 2 non-isomorphic, they are not isomorphic, trees with 3 vertices. Okay. Okay, and unrooted, all unrooted trees with 3 vertices look like this, and rooted ones are these two ones. Okay, and here we have the question 6. Okay, we will, this is again homework for you. We will find the minimum height, okay, of a full binary tree with 80 vertices. So we will use some theorem here. It says if you have a tree which is full binary tree with n vertices, then n, which is the number of the vertices, n should be less than or equal to this 2 to the h of h plus 1 minus 1. where h is the height. Okay, so we know we want to find the minimum height for the tree with 80 vertices, so n equals to 80. Then 80 should be less than or equal to this, 2 to the h plus 1 minus 1. Then we have, using this inequality, we get this, 2 to the h plus 1 is greater than this. We see that 2 to the 6 is 64, so it's less than 71. Then if h is equal to 6, we will get the minimum value for this 2 to the h plus 1, which is greater than 71. So h should be equal to 6. So the minimum value, minimum height for such tree is 6. Now we will find the spanning tree, okay, for the given graphs. Okay, we will remove the edges. Okay, so here we have, for example, this is one of the spanning tree. It is connected, obviously. So we remove the edges, this one and this one, right? This is not a tree, right? This is not a tree because it has two circuits. Okay, it is connected but has circuits, so it's not a tree. But if we remove them, this edge and this edge, we will get this graph. Okay, this graph. So it is connected, still connected, and it has no circuits, right? And it's contained in the graph, in the exactly given graph. So it is a tree. So it's a spanning tree of this graph. Okay. And another one is for B. So here we have. So we had before this one. Okay. We removed some of the edges and get this tree. It is again connected. There is no circuit. It's a subgraph, right, of the given graph, right, of this. We have the same edges, right? Let's draw it on the given graph. Okay, here we have A. Here we have okay, so here we have this edge and this, and then this, and finally okay, I made a mistake there. This is not a subgraph, right? Because there's no edge between A and F, but we can write it like this. For example, this, okay? So it is connected, right? There is a path between any two vertices, and it's connected. So we said that, and there is no circuit, and it's a subgraph, right? Because any edge on this new graph is contained in the previous one, so it's a subgraph. Thus, it's a spanning tree. Okay. So another one for this graph again is this. Let's write it. So here we have from this, this, and this one. This is also a subgraph, right? Because each edge is contained in the previous one, and there is no circuit, it's connected, so it's a spanning tree also. Okay, so this is a homework for you again. Now let's find the last one. Here we have. So again, if you read the question, you will get that we need to find a subgraph of this graph. Sorry, not only a subgraph, but a spanning tree actually. Okay, because we want to reduce the flights. So, for example, we can do something like this. So the spanning tree should be a subgraph. So don't forget that. For example, this is a subtree, a spanning tree. Sorry, this and this. From Denver to Chicago and Detroit, we have an edge between them, so we can use it. And from here to Atlanta, to Washington, New York, Houston, and Denver. So this is a subgraph of the given graph, right? So it's connected, right, from any two vertices. Between any two vertices there is an edge, so there's no circuit. For example, if we drew this, we drew something like this, we drew an edge between them, then we would have a circuit between them, so it wouldn't be a spanning tree. Okay, so but this is a spanning tree, so this is one of the solutions. Or we could write something like this: from Seattle to Chicago. Sorry. Chicago and Detroit, New York. Then we have the same. Okay, to Atlanta. And then San Luis. And then Denver. This, and this. Okay, so this is also a subgraph, obviously, and it's connected, and there's no circuit, so it's a spanning tree also. And this is another solution, for example. Okay, this was the last question. Hope you understood. So if you have again any question, you can attend the office hour on Friday. See you there.